Bismillahirrahmanirrahim. Assalamu alaikum. Dear students, welcome to another lecture of Physics 2. This is lecture number 6 of the course. In this lecture, we will cover the remaining topics of chapter number 17. The name of the chapter is Sounds. Our main topics of today's lecture will be the beats phenomena, and this phenomena is also known as the interference phenomena in time. Our second topic will be the Doppler effects, and we will study the cases in these effects when the observer are moving and the source is stationary, and the second case when the source is moving and the observer are at rest. So these two cases will be studied in this lecture, and our final topic will be the supersonic sound, when the speed of sound exceed from the speed of sound in air. So these sounds will call the supersonic sound. So let's start our first topic, which is beats, and this beats is the interference phenomena in time. Consider two waves of slightly different in frequency passing through a same region of space. So they will interfere each other, and the resultant wave will produces in such a way that there are some parts of the resultant wave where the amplitude is high, so we will hear a loud sound in that part, and there are some other parts where the amplitude is almost equal to 0, so at that point the sound will be faint. So the periodic alternation between a loud sound and a faint sound is known as the beats phenomena. So in the figure you see that there are these places where the amplitude is larger, so a loud sound will be here, and after this the sound is vanished and we say that the sound is faint, and again we will have a loud sound and then a faint sound. So there is the periodic alternation between loud sound and a faint sound is known as beats phenomena. Or if two sound waves of very slightly difference in frequencies moving in a same medium produces periodic increasing and decreasing in the intensity of sound is known as beats phenomena. And for this we take two time dependent variation of displacement due to two sound waves of equal amplitude, which is Sm will be, let S1 is equal to Sm cos omega 1t and S2 is equal to Sm cos omega 2t. So as the beats phenomena is the interference phenomena in time, so the time parameter is remain the same, and only the frequency omega 1 and omega 2 will be slightly different from one another. The amplitude term is the same, so with the condition omega 1 which is slightly greater than omega 2. So we will proceed to our resultant expression. So by applying the superposition principle on our initial expression, and we will get the resultant expression, which will be the algebraic sum of the instantaneous displacement. So S represent our resultant wave, which is equal to S1 plus S2. By inserting the value of S1 and S2 here and taking Sm as a common, so we will have cos omega 1t plus cos omega 2t in the brackets. Now by applying the trigonometric identity, which is cos alpha plus cos beta equals to 2 cos alpha minus beta divided by 2 into cos alpha plus beta divided by 2. Here omega 1t will be our alpha term and omega 2t will be our beta term. So by putting the value of alpha and beta in this trigonometric identity and then insert this result into the above expression, our resultant wave will be S is equal to 2 Sm cos omega 1 minus omega 2 into t divided by 2 into cos omega 1 plus omega 2 into t divided by 2. So in order to obtain the expression with which we start our phenomena, so we will define omega prime, and omega prime is equal to omega 1 minus omega 2 divided by 2 and omega, which is equal to omega 1 plus omega 2 divided by 2. So our beat frequency must be related with this term. By inserting omega prime instead of omega 1 and omega 2 divided by 2, our resultant will be like the expression with which we start this topic. So S is equal to 2 Sm cos omega prime into t cos omega t. So the amplitude of the resultant cannot be exceeded with the 2 Sm. So the amplitude of the individual or the amplitude of S1 and S2 is Sm, but the amplitude of the resultant may be up to 2 times Sm. So this expression is just like S1 and S2. So now discussing the beats frequency in the next slide. So our resultant expression, which is equal to 2 Sm cos omega prime, which contain the beats frequency omega prime into t cos omega into t. Remember that here are two frequency. This will be the frequency of the resultant wave with which it travel, and this is the frequency with which there is rise and fall in the sound in one cycle. So this is the beat frequency and this is the frequency of the resultant wave with which it travels. And remember that this omega is much greater than omega prime. So let's define our beat frequency. The angular frequency omega beat at which beats occur is given by omega beats, which is equal to 2 omega prime, and in previous slide we defined omega prime, which is equal to omega 1 minus omega 2 divided by 2. So here 2 will cancel with this 2. So omega beats is simply equal to omega 1 minus omega 2. So if you convert these angular frequency with the natural frequency, so we will put the relation omega, which is equal to 2 pi f. So if we insert 2 pi f beats over here and here 2 pi f1 minus 2 pi f2, so 2 pi will cancel with 2 pi from the left and right hand side. The 2 pi will cancel. We will have the beats equation in the form of natural frequency. So f beats is equal to f1 minus f2. So to understand this phenomena, so let us consider we have two tuning fork with frequency f1, which is equal to 552 Hertz, and we have a second tuning fork with frequency 556 Hertz, and if they are hitting simultaneously and produces sound, and they are then allowed to move in a same medium, so the beat frequency will be equal to 4 Hertz. And remember that this is the periodic rise and fall in one cycle. So in one cycle there will be 4 loud sound and 4 faint sound. So the average frequency of the resultant will be 552 plus 556 divided by 2, but the beat frequency will be 4 Hz, which will be the 4 loud sound and 4 faint sound in one cycle. Our second topic of the lecture is the Doppler effects. In this slide we will define the Doppler effect and will study its validation. When the source and the observer is at rest, then a source emits sound with frequency f, and the wavelength of the sound is lambda, and it reaches to the stationary observer with velocity given by v is equal to f lambda. So this is the velocity of the sound when both the source and the observer is at rest. The frequency of the sound at that time is f, and the wavelength of the sound is taken as lambda. But when the source or observer, if they are moving toward each other or away from each other, and the source emits sound, so in that case the frequency will be changed, and this phenomena is known as the Doppler effect. So we will define as the change in the frequency of the sound due to the change in the relative motion of the source and the observer is known as Doppler effects. The Doppler effect holds not only for sound waves but also for electromagnetic waves, which including microwave, radio wave and visible light as well. So the validation of Doppler effect is also valid in the electromagnetic waves. So let's study the cases of the Doppler effect. The first case, in which the detector is moving while the source is at rest, or the observer is in motion while the source is stationary. So let's define some parameters. When both the source and the detector are at rest and the source emitting sound, the speed of sound is taken as v, the normal frequency is f, and their corresponding wavelength is taken as lambda. So these are the parameters when the observer and the source is at rest and the source emitting a sound. So v is equal to f lambda, and by solving the expression for lambda we will have v divided by f. So in the figure, S representing the source, which is in this case at rest, while the observer, whose speed will be Vd, and the observer can move away or toward the stationary sources. The spherical surface represent the spreading of sound in all direction, and between the two consecutive surfaces the space represent the wavelength. In this case this is the normal wavelength because the source is at rest. So if the source is moving, we will use Vs as the speed of the source, and the detector speed or the observer speed is taken as Vd. So when the observer moves toward the stationary source while the source is emitting sound, so the observer will feel that the speed of the sound is greater than the normal speed of the sound because he is moving toward the source with speed Vd. So relative to the observer, the speed of the sound is equal to Vd plus V, or V plus Vd. So this change in the velocity will cause a change in the frequency, which is given by f prime is the change in the frequency, or this is the frequency which is detected by the observer, and this is change from the normal frequency because the speed of sound relative to observer in this case is increases from the normal speed of sound. So for f prime we will use v prime divided by lambda. The lambda is the same. So when we insert the value of v prime, which is equal to v plus vd, and also inserting the value of lambda, which is equal to v divided by f. Now by solving this expression we will have f prime, which is equal to v plus vd divided by v into f. Now let us understand that what this equation represent. So v is the speed of sound, vd is the speed of the detector, and this is the normal frequency when observer and the source were at rest. So it is clear that the upper velocity term is greater than the denominator term. So the coefficient of f, the coefficient of the normal frequency in this case will be greater than 1. So this frequency f prime will be greater than f. So in this case, when the source is at rest while the detector is moving toward the source, so the observer will hear a sound with frequency f prime which is greater than. So when the observer is moved away from the source, so he will feel that the speed in this case is less than speed of sound. The speed of sound in this case is less, so he will minus his own velocity. Again the frequency will change, and in this time the frequency will equal to v minus vd divided by v into f. So it is clear that the upper term is less than the lower term, so the coefficient of f in this case will be less than 1, which is clearly indicated that f prime will be less than the normal frequency. So if we combining the both cases in a single equation, so we can write f prime, which is the change frequency due to the relative motion of the observer, will equal to v plus minus vd divided by v into f. The plus sign is for the motion of the observer which is moving toward the source, and the negative sign is the case in which the observer is moving away from the source. In this slide we will discuss the second case of the Doppler effects, in which the source is moving while emitting the sound as well, and the detector or the observer at rest. So again we consider that when both the source and the observer is at rest, then the normal parameters are v, f and lambda, which is given by v is equal to f lambda. And if we solve this equation for lambda, we will have v divided by f, and here we use the definition of time period. So lambda can be written as v times time period, because in this case we, from the figure it is clear that when the source is moving toward the observer, so at one side of the source the space of the spherical surfaces is reduces, while on the other hand the space between the spherical surfaces increases. So in this case we will discuss the wavelength. So due to change in wavelength there may be a change in the frequency which is detected by the detector. So now When the source is moving toward the detector and the speed of the source is Vs, so the wavelength of the sound waves will be decreased. So as the source moves toward the observer, the wavelength of the sound will be decreased by Vs into t times, and the frequency will change. So our change frequency is represented by f prime, which is equal to v divided by lambda prime. This v is the speed of sound when both the source and the observer were at rest, and in this case, as the wavelength change, so when the wavelength change, there will be a change in the frequency of the observer. So by putting the value of lambda prime, we will get f prime is equal to v divided by vt minus vs into t. By taking common the t terms from the denominator, we will have v divided by v minus vs into t, and here the reciprocal of time period is frequency, so the change frequency expression will be equal to v divided by v minus vs into f. Here it is again clear, this v which represent the speed of sound and this vs representing the speed of source. So the denominator term is smaller than the numerator term, so the coefficient of f will in this case will be greater than 1. So when the source is moving toward the stationary observer, the observer frequency will be higher than the normal frequency. So f prime is greater than f in this case when the observer is at rest and source is moving toward the observer. But when the source is moving away from the detector, then the wavelength which is detected by the detector is increased by Vs time t. So the change in the frequency in this case will be equals to V divided by V plus Vs into f. So if you compare this expression with the above one, where the denominator term is smaller than the numerator term, in this case the denominator term is greater than the upper term. So in this case the ratio, the coefficient of frequency is less than 1. So in this case the frequency which is detected by the detector must be smaller than the normal frequency, and these two equations can be represented by a single equation by inserting the minus plus sign. So the minus sign will show us that the source is moving toward the observer, the stationary observer, and the plus sign will show us that the source is moving away from the stationary observer. So these are the two cases in the Doppler effect in which either source or either the detector are moving with respect to one another and their frequency will be changed from the normal frequency. Our last topic of the lecture is the supersonic speed, and we will also discuss the generation of the shock waves. In the adjacent figure, two different situations are being presented. In first case, the source S which is at rest and emitting the sound which is spreading uniformly. The spherical surface represent that the sound are spread in all the three dimensional, and in this case the wavefront are well away from the source. But when the source start motion with the speed equal to the speed of sound, then this source S will move along the surfaces. So Vs represent the speed of sound in this case, which is moving toward the right, so it will move parallel to the wave front. And if the speed of source is exceeded to the speed of sound, then we will call it the supersonic speed. So we can define as if the speed of a source relative to medium exceeds the speed of sound is known as the supersonic speed. And with such a speed, the Doppler's equations which were developed earlier are no longer applicable with such a high speeds, and all the wavefront bunch along a V-shape envelope. The bunching actually form a cone called the Mach cone. So when the speed of the source exceeds to the speed of sound, so they will form a V shape which is called a Mach cone. And in this slide, this cone has been shown. When the speed of the source exceeds, so the wavefront will be left behind from the source, and this is called the Mach cone. And the shock waves exist along the surface of this cone because the bunching of wavefronts causes an abrupt rise and fall of the air pressure as the surface passes through any point, which will form a shock wave. And the half angle of the cone is called the Mach cone angle and is given by sin theta equal to Vs divided by V. If this is the full angle of the cone, so the angle made with the horizontal line is known as the half angle, or which is known as the Mach cone angle. And as Vs divided by V is the ratio of the same quantity, which are the velocity, so it will give us a number, and this number is known as a Mach number. So if a jet plane move with a Mach number 2, so it will tell us that the speed of the jet at that time is twice the speed of sound. Or if a jet plane is moving with a 2.3 Mach number, so this means that the speed of the source is 2.3 times to the speed of a sound, and so on. So let's sum up our lecture number 6. We have studied the beats phenomena, which is the interference phenomena in time when two waves of slightly different in frequency passing through a same region of space in same time, so their interference will produce the beats. And the beats are actually the periodic alternation of sounds when the sound has a maximum intensity and zero intensity. So that phenomena is known as the beats phenomena. We have also discussed the Doppler effects, which the frequency of the observer is changing due to the relative motion of either observer or by the source, and we have discussed these cases and derived some valuable equations. And our next lecture will be about thermodynamics and temperature scales. So I hope that you will understand this lecture, and you can contact me at my email if you feel any difficulties or if you have any question related to this lecture. Thanks, and Allah Hafiz.